European Web Center.
Thanks, Hilary. Yeah, so as I said before, this is some very much work in progress. So from that point of view, it has very little flashy pictures. You know, I mean, to some extent, that they were last week in my presentation at the PDS Sphere. So this is really to spin this thread of using anelastic or the combination of hydrostatic anelastic a little bit further, and how it would sort of impact an operational NWP model, and what maybe we would gain either in terms of efficiency or accuracy if we were to go to you know, a sort of hybrid hydrostatic anelastic formulation. And so yeah, basically I would like to discuss some of the theoretical aspects mostly and especially in the context of the spectral transform model IFS. So the starting point really is the hydrostatic primitive equations that we currently still solve in our operational system, and with which we produce the deterministic high-resolution forecast. Now we have a non-hydrostatic system as well, but one of the drawbacks, the big drawbacks of this non-hydrostatic system, is the fact that it is twice as expensive, and I'll come to this a little bit later. And the beauty about the hydrostatic primitive equations is that if you heard Darrell Holmes talk yesterday, who was talking about a sort of a Lagrangian of your climate, if you like, that I believe that these hydrostatic primitive equations provide this Lagrangian. They provide really the background for around which you could devise more accurate numerical methods that would allow you to sort of predict the weather, and maybe you know, make breakthroughs even on the sort of seasonal prediction, where currently we are very, very poor. If you were to devise something that you know very well, and now how do we extend it to the non-hydrostatic regime, basically? So we have difficulties giving up this equation set, if you like, because they are so efficient, and you can get this hydrostatic large-scale answer very fast, and arguably the most, you know, in the fastest way possible. So how can you use this information in a model that allows you to also resolve finer scales? So the current approach that had been taken by development at Météo France, where it started off with publications by Bubnova in 1995, they developed a non-hydrostatic core which was initially designed for limited area modeling, and it was based also around the idea of having to change very little in the hydrostatic system, but to include basically a distinction between the hydrostatic pressure on the one hand and the total pressure, which is defined by P equals rho over RT on the other hand. And so the way this system was designed was by introducing a non-hydrostatic pressure departure, here expressed in this variable Q hat, as a logarithm of the true full pressure and the hydrostatic pressure pi, which you would predict from the hydrostatic system. And the geopotential in the system is derived from RT over P, whereas in the hydrostatic system it would be derived from RT over pi. Okay. But this system, which is the NHS, or non-hydrostatic shallow atmosphere, so let's not worry about the deep atmosphere for the moment, because at least for the application that we're running at the moment, we don't really, we have also got a deep formulation of this non-hydrostatic system, but we don't really see any differences except in cost, and therefore it seems reasonable for the Earth to continue with the shallow atmosphere approximation for the moment, at least for the depths that we're resolving. And in any case, the issue, I think, that comes with going to the non-hydrostatic system in this framework is the fact that you now have this three-dimensional divergence, which contains the horizontal divergence, which is all we had, if you like, in the hydrostatic system, and it was all kind of nice and sort of easy. But now you get the influence of this vertical divergence, or the influence of the vertical velocity, that you now have an extra prognostic equation for. And if you think about the discretization in the vertical, where in IFS we have a distinction between where we keep the variables on full levels or on half levels. There is not really a staggering, except that the pressure lives on the half levels between like the full levels, where we keep all the prognostic variables. So then the natural choice, in fact, to stabilize this model, because I had a lot of issues in the beginning in designing this non-hydrostatic model with stability, was to go to a prognostic variable which was in fact the vertical derivative of vertical velocity, in order to move it also to the full levels where the other prognostic variables live. But this has implications in terms of how you, sorry about this, how you treat the sponge layer. And so there's, you know, there are issues with this variable, and we would like to really have a vertical velocity as a prognostic variable in the system. Now, if you have a z-coordinate, this is maybe a little bit easier, but because this has evolved from a system where we use pressure, or in fact a form of hydrostatic pressure in the vertical coordinate, which has been initially started in a paper by Laprise in 1992, then you essentially move to a system from a fixed coordinate z, which is independent of time, to a coordinate that depends on time. So then if you take the evolution of this 3D divergence and write it in general curvilinear time-dependent coordinates, you end up with an extra term. And that is in fact this x term, which expresses the horizontal gradient of geopotential times the vertical derivative of the horizontal velocities. And this term is ugly. And in fact, in the current non-hydrostatic discretization of the IFS model at least, this term gives rise to instabilities. And we had to do some trickery, in fact, to stabilize the non-hydrostatic system and compute this basically along the semi-Lagrangian trajectory, and then there were ways to stabilize it. But it's, you know, not very desirable. So this system of equations then is sort of written in a simplified form like this. And the other aspect that I would like to stress here is that when you run numerical weather prediction models at the scales that we are running, you have to couple it to physical parameterizations. So the issue, I think, arises when you have a fully compressible model and you have a predictive equation for the non-hydrostatic pressure departure. When you formally derive those equations with physics included, then the last equation at the bottom, which is this equation for the non-hydrostatic pressure departure, has also physics on the right-hand side. So it has like this extra term. Now the problem with that is really that your physics, at least in our current system, have been designed at constant pressure. So also we have a vertical coordinate which are the pressure levels. So the physics is not really allowed to change this pressure. There is not really any sort of physical tendency that directly from the physics in our physical packages that change the pressure. So this in unelastic models, this question doesn't really arise because you project everything onto temperature and the velocities immediately. So we did like a test where this is actually work by a colleague of mine, Sylvie Maladel, where we consider two different kinds of coupling to the physics. One like in a compressible way, and you see in this graph here the blue line is the dynamics and the total is in red, and the dark blue line is the physics. So if you do this sort of compressible coupling, then you see a little bit of a difference between the physics and dynamics. Whereas when you do this unelastic type of coupling, which I come to in a minute what it means, essentially you get this residual instantly, whereas the other one sort of arises over about 15 minutes, basically. So in fact, when you look at these tendencies again, what we do, in fact, when we run the non-hydrostatic model now, we actually, even though algorithmically you can argue this is incorrect, we remove this term. We don't put any physical tendencies on the right-hand side of the pressure equation, because part of the problem is when you run this with large time steps, this actually creates instabilities. And so what we learned from this experiment, basically, is that you know, the unelastic coupling on the one hand is the non-hydrostatic pressure departure instantly converts the volume change without the sort of, if you like, resolved computations of the dynamics. And in the compressible case, the physics is allowed to change the non-hydrostatic pressure departure, but can still not change the mass distribution because you haven't changed your vertical layers. You know, there's nothing that changes the surface pressure. So therefore, the mass rearrangement can only be done in the dynamics, because once you've done like your solver with your semi-implicit system and connect everything together, that's when you start to change the surface pressure. So to cut a long story short, it still seems more stable to simply just remove the term on the right-hand side, and it gives also the best results in some sense. Now, this is very heuristic, but the coupling with the physics raises really the question whether since the physics, I should point out, are very, very important at the sort of scale that we're running at in numerical weather prediction, it raises the question whether fully compressible dynamics are really needed at all, because the physics are coupled in some sort of unelastic way anyway. So working towards a unified hydrostatic unelastic system, then scientifically, the benefit of having this prognostic extra equation for non-hydrostatic pressure departure is, at least to me, unclear. And there's another thing that in the current numerics is used to stabilize the system with respect to the existence of the vertically propagating acoustic waves, and that is that the system uses two reference states in the semi-implicit solution procedure. And one uses a reference temperature that's specifically designed for the gravity wave term, which has to be warmer than any exists, at least in a two-time level scheme. There has been a paper written about this, why this is. But it has to be warmer than any temperature that occurs inside your model. But for the acoustic waves, it turns out, there has been a paper by Pierre Bernard, it has to be colder than any temperature that occurs in your system for the acoustic waves. So you have this discrepancy. And in fact, it turns out that when you run it for real systems, you run this non-hydrostatic code, that your ability to tune these reference temperatures is quite limited. Because if you go too cold, it gets unstable. If you go too warm, it gets unstable as well. So for the acoustic waves, there's a very limited temperature band, I would say, where you can get a stable integration when acoustic waves are present. And that's undesirable as well. So I mentioned already the coupling to the physics is somewhat ambiguous. And then for stability reasons as well, the non-hydrostatic system requires at least one iteration. So I'm washing a lot of dirty washing here, I realize. But that's what we currently have, if you like. So we need two iterations, which means in a spectral transform model, you have to repeat all your spectral transforms within one time step. So you do all the transforms twice, which adds to the cost. Now I've shown that we have now developed this fast Legendre transforms. That's great, and that cuts down, compared to the hydrostatic simulation, the cost by more than half when you go to 2.5 kilometers. So that's all good news. But still, doing less transforms will be better. And I think in the past, people got very excited about removing just one by doing a clever transformation like Clive for example, evaluating the derivatives. There were papers where when you removed one transform or needed one less, this was a major improvement of the code. And I will show you that when going to a quasi-anelastic hydrostatic framework, there is the possibility of removing 7 transforms per time step. So that's quite exciting, at least from a spectral perspective. And the last point, it appears that when you use split explicit, like heavy time schemes, and I'm glad Joe is here, he can maybe confirm that if I read the paper correctly, but they apply a 3D divergence damping by essentially adding what I think is like a penalty term, which implies or enforces a form of unelastic balance in order to stabilize the split explicit time integration schemes. And that's very much, if you look at the term, it's actually mentioned in the paper. It looks like the continuity equation of the pseudo-incompressible system. Then I should also mention the further development of Rupert Klein of the classical scale analysis of Gura and Phillips, where they said that the inelastic equation has to be done or can only be used for models with temperature variations within like a few degrees. And this has been substantially extended to maybe something like 30 to 50 degrees with modern scale analysis. So I believe that it would certainly allow very general applications if these perturbations were around a time-dependent background state, which is something that has been alluded to in Piotr's lecture earlier this morning. So now coming to this unified system of Arakawa and Konor. So the goal really here is to design a special density in the continuity that filters acoustic waves without compromising the rest, and in particular the large scales, while maintaining the total energy of the system invariant. So Lipps and Hamler did this by introducing a background density that just depends on the vertical. In the Durand system, there was a special density rho star that was a background density times the potential temperature variant in the vertical. And Durand, in some later publication, mentioned that really they all like part of a larger class of densities, which are of the form rho tilde theta tilde over theta.
Actually, this is not just in Lipps-Hamler that this is density dependent on Z. It's a special density that comes with the expansion around the constant stratification profile of potential temperature. Because in Ogura and Phillips, the density also depends on height.
Okay, but it's different from Business where it's constant basically. So I see. Yeah, I agree with that. And there are different variations of inelastic models which do it slightly differently. In fact, you know, they just they all boil down to a very similar formulation as far as Lipps and Hamler goes. But the interesting point here with the Arakawa and Konor system is that this, if I design this density to be pi over RT tilde, where my T tilde is just the temperature multiplied with 1 plus Qx to the power minus kappa. So if you like, 1 plus Qx is ln P over pi, which is a Q that you saw earlier. So really, this tilde refers, and when you see tildes now from now on, they are really like the true values times e to the power minus kappa q. So all my tilde variables are basically scaled with e to the power minus kappa q. Okay? And this is actually something Olaf Stiller pointed out from DWD when he was still at ECMWF. And he said, why don't you use this variable? And I thought, yeah, great idea. Because it's a great idea because it doesn't change anything in your hydrostatic system. Without approximation, you can now write the thermodynamic equation exactly like you had it before in your hydrostatic system. It's exactly the same, it's just in T tilde. And there's no approximation here. So this is like in the Arakawa-Konor system as well. They don't change the thermodynamic equation at all. They solve d theta dt equals 0. The approximation in the unified system of Arakawa-Konor, translated into my pressure coordinates, if you like, is the fact that you change the continuity equation and this into a 1 over rho qs d rho qs dt. Now, if you don't make any approximation, you will get this equation with this gamma sort of term, where you have this k minus 1, 1 plus qx, d 1 plus qx dt. The essence of the Arakawa and Konor approximation is to set this to 0. So setting this to 0 means also that it influences the way you predict, because it appears again, because it comes to the continuity equation, it appears again when you derive the surface pressure and when you derive your vertical velocity eta dot if you use an eta system. So also there, you have to set for consistency this gamma to 0. And then, in addition, when I do now this transformation from the z-coordinate system into the pi coordinate system, I use this rho qs also in the transformation of my variables. So this has consequences for the geopotential. My geopotential d phi d pi is now minus RT tilde over pi. So it is 1 over rho qs, essentially, for the geopotential. And then I arrive at this set of the equations, which has the nice characteristics, and when you look at the tilde variables, they are almost isomorphic with the equations in the hydrostatic system, plus this epsilon plus 1 forcing term, obviously, in the horizontal geopotential gradient, and the 1 plus epsilon on the right-hand side of the W equation, plus this extra term e to the power minus kappa q that comes in here again. But the thermodynamic equation hasn't changed. It's just in T tilde. It's a name change of the variables. And you have this extra equation for the divergence that connects the divergence and the vertical velocity in order to close the system. So when you do a linear analysis of this, as we in fact do when we derive our semi-implicit system, we linearize the equations around an isothermal basic state. And then we subtract this linear system from the fully nonlinear system and solve the nonlinear minus the linear one explicitly and solve the linear part implicitly. That's how you derive the semi-implicit system in the case of, like, you know, how we do it in IFS. So when you do this and then X out all the variables, you end up with this single equation for the vertical velocity. And it's interesting that this structure equation is identical to the Lipson-Hemler system. And so it gives like the same behavior as, for example, the ULAC model in this context. And it is the same as in the unified system as well. Now, this might be specific to the fact that we do this variation around an isothermal background state. That I'm not sure, because we discussed this, I think, at some point. And it may be specific. But obviously, for the design of our semi-implicit system, this is what we do. So when we have the correct structure equation, if you like. And the additional benefit of this system is that at large scales, it obviously collapses to the original hydrostatic system. So the system, in fact, is energy invariant, as far as I can tell. Now, there is a bit of a conflict that I see here with the original paper by Arakawa and Konor, who have to apply an averaging over the pressure departure in order to achieve this energy consistency. Now, for some reason, I don't have to do this. I don't know why. But when I apply the analysis exactly like in the paper of Laprise with these tilde variables, I arrive basically at this energy equation that you see at the bottom, and the right-hand side term vanishes with appropriate boundary conditions integrated over the volume, because you know, P at the top is 0 and phi at the bottom is the surface. It's not independent of time, so the right-hand side vanishes. And the only change to the hydrostatic system, if you like, is this P over pi times RT tilde, which enters the energy term. So it slightly modifies, basically. Instead of CPT, you have a modified version, which is CPT minus P over pi R. So there's a weighing, basically, of the CP in your energy. But nevertheless, even though it has a different form, it has an energy invariant. So then the solution procedure proceeds like this. You do exactly the same as you do in your hydrostatic system. So if you don't want to solve the non-hydrostatic system, you're finished here. After solving this equation that you see here at the bottom, where you have to invert this right-hand side coefficients in spectral space, so I'm reminding you that the...
If you show this on the screen, we don't see what you're doing.
Sorry. Yeah, so reminding you that the Laplacian in spectral space is just n plus 1 over a squared. So when you solve this equation for the wave modes, for each wave number, then this results in a constant or different one for each wave number. But you have to sort of, these are matrices, these are vertical operators, which I can show on the next one. So these are these vertical operators here. So if you, as long as you have positive and real eigenvalues, and we in fact have, then you can invert the system and solve for the variable d. Now in the non-hydrostatic system, or which I might call your iteration 0, you have this non-hydrostatic pressure departure, this ln p over pi here, or the Laplacian of it rather, on the right-hand side. So you get an extra forcing basically on your divergence. So this couples, if you like, your non-hydrostatic system to the hydrostatic system. So these are these operators. They're linear. So when you derive this equation then further in the unified system, you get this extra relationship between W and Q. And you end up with one linear relation for the W equation and the D. And you, unfortunately, and that's like, if you like, the issue, end up with a nonlinear relation from the continuity equation which relates the D and the W again. So in order to eliminate the system, you don't end up now with a system where you have a single equation which only has linear operators. But that's what you want in spectral space, because otherwise you can't solve the system. So the way I proceeded with this for the moment is that you take the linear relationship for the continuity equation. This is perhaps something that Piotr also alluded to earlier, that you have to do some form of linearization. But then you can arrive basically at the same structure equation that you saw earlier in your discretized system. And this you may view as your preconditioner of a iterative procedure where you solve the full nonlinear problem. So you can solve for this W and then sort of take a more complicated view after this. So then through back substitution you can recover all the other variables. So just to give you an idea where this could benefit us also is when you have, this is like a pie chart showing the distribution of the cost of the hydrostatic model at T2000 resolution, our next operational resolution, and this is at 1279. So at hydrostatic resolutions, we spend very little in the transforms, we spend very little time for the spectral computations, i.e. this solution of the Helmholtz equation that I showed earlier, xing all this out, that's just like 4% of the whole cost. So it's very powerful in solving this elliptic equation. It's solving a semi-implicit system, costs nothing basically once you've paid the 9% to transform into spectral space. But in the non-hydrostatic system, now when we step from T2000 to T4000, you suddenly see 23%. The transform is actually not too bad, it's only 22%. But suddenly we see this 23% in the spectral computations. Now this is because the non-hydrostatic system is much more expensive in solving this Helmholtz equation, because it has to do things twice and it's all very, very cumbersome. It's not as easy as I've just shown earlier. So the reason really for this blow up in the cost is the fact it doesn't parallelize very well. Because of this complication in the system, now you get a relationship, a dependent relationship between wave numbers n, n+1, and n-1. So you can not only, currently in our hydrostatic system, we parallelize over the wave numbers m and n. So we have a large space to parallelize. But in the non-hydrostatic system, we can only parallelize over the m. So you run out of parallelism. So when you go to these large wave numbers, you basically, you see this. And that's this extra cost. So this anelastic system would give us this extra benefit of reducing this back to the hydrostatic system. So these are specific gains that I believe could be very beneficial in pursuing this route further. So you remove these acoustic modes, you have W as a prognostic variable. I said potentially saving 7 spectral transforms, +1 in fact, per time step, because I don't have to do everything twice anymore. I have to, but it's the price is solving this extra elliptic equation basically. And yeah, remove this parallelization bottleneck, and there also, that's a side issue. We don't have to mention this now. So yeah, I'm finished really, and that leads into some discussion points for the next part. Thank you.
I think Nils can take a few questions, and then we'll stop so that people don't have to stay for an extended discussion session. So, any questions?
About comments. So I had a thought while listening to your talk. The formulas of tensor analysis allows to transform just purely mathematically from one system to another, to arbitrary curvilinear systems. But there is an assumption behind that you have to know your general form of the equations. So if you don't, in one system, if the equation is abbreviated and you transform to another curvilinear system, there may be missing terms. The good example is if you do mass continuity in time-dependent coordinates. You start with like an incompressible or anelastic mass continuity, you finish and you just transform through chain rules. You lack the term that looks like a compressible term. This is you know what I'm talking about. So I had this thought that maybe it would be worth revisiting this Laplace system by taking general form of compressible equations, in arbitrary curvilinear system, and assume that there will be the time-dependent coordinates will be this isobaric, and redo it in this way to check if there are no terms missing. You know what I mean?
But I started from the z-coordinate system, right?
Well, we started with hydrostatic, somewhere with hydrostatic.
No. I started with the I started with the Euler equations, basically. I started with the Euler equations, and the transform into this Laplace coordinate, if you like, was done starting from the Euler equation and the z coordinate. The only change I then introduce is this approximation to the continuity equation that I say, instead of 1 over rho d rho dt equals divergence, I say 1 over rho qs d rho qs dt equals divergence. So in fact, I've derived, if I've done it in fact differently, in a sense, I've derived the full equation without throwing anything away. And then you have them all, and then you start to remove the gamma brackets.
But you started in particular system, in Cartesian, with Euler equations,
That's
but
correct.
you could start with Euler equations in arbitrary curvilinear time-dependent system, and then transform. This is what I'm talking about.
But you have to end up in the same place.
If you start with the correct equation, yes.
Well, but don't you accept that the equations in Cartesian form are correct?
No, it's
So you
not
question
true.
that as well. Okay.
No, it's not true. I'm not. It's not. I can give an example. If you start,
I think this has become discussion. Are there any more questions very specific to this talk before we call it discussion? People who don't want to stay for this discussion, I'm going to give you a minute to leave. And also, I'm not chairing it anymore.